All right, so this is the K Unit 5 Momentum and Impulse CFU from class today that I'm just going to kind of click through and we can answer whatever questions you guys have on it. If we get to one, you know, like we got this, or we can just speed through it. But this is number 1 on my version, and it says, which of the following has the greatest momentum? And so for this one's pretty straightforward. Your momentum calculation is just momentum is equal to mass times velocity. So that's all you're doing here is you are comparing these. Each of them provides you a mass and a velocity, and you're just looking for the one that's going to give you the greatest value when you multiply them. Looking at these, I can tell that it's either going to be this one right here or this one, just because those have the biggest combinations of numbers. So let's go ahead and figure out what those two middle ones are. 3150 times 19.
Students and teachers, it is 2:55, which means that all students should be with their club sponsors, their teachers and tutorials, or their coaches. There should be no students in the hallway unattended. Students, if you are in the school or in the hallway without an adult, you need to leave. It is time to go. Go Bears.
All right, so that is all that I just did. I'm trying to get the glare off of it. Is I just checked those two middle ones. Like the last one was no point checking because both those two numbers are smaller than these two, so I didn't even bother checking it. Same idea here. So looking at the middle two, the one that's going to give me the greatest product is 1500 times 43. So that's all you had to do there was that basic momentum is mass times velocity calculation. The second question on mine says a 3.95 times 10 to the third kilogram car traveling north is slowed down uniformly from an initial velocity of 34 meters per second by a 6,900 Newton braking force acting opposite the car's motion. What is the car's final velocity after 14.1 seconds? I believe there is a question like this on the test, and then you've seen this question before as well in the problem sets. So let's go ahead and start by labeling the information that's been given to us so that we can better analyze it. That mass, 3.95 times 10 to the third, is the same thing as 3950. I'd prefer to write it in standard form. So I'm going to write it like this, 3,950 kilograms. I know that I have an initial velocity, VI, of 34 meters per second, that I have a braking force, which is going to be my net force because the car is slowing down. You're not going to be pushing your gas and your brake at the same time, so the only force acting on it is going to be this braking force. It is opposite the car's motion, so I am going to put a negative sign in front of it, and I'm going to write 6,900 newtons. And then it wants to know what the final velocity is after a time of 14.1 seconds. So that's the information that's given to us in the question. Looking at this, you have some options here. The first thing that you might notice is that you have a force and a mass, and thus could find acceleration using F net equals ma. And then you could use kinematics if you wanted to. That's option 1. Option 2 is to use one of these new equations that we learned this unit. F times t, that's impulse, equals m times delta v, that's change in momentum. And you can use that because of the information that you have, and this would allow you to do that in one step instead of two, and so that's what I'm going to do. I'm going to take my force, negative 6,900, I'm going to multiply it by my time, 14.1, set it equal to my mass, 3,950, times, now delta v, I can either solve for delta v and then figure out my final velocity after that, or I know that delta v, change in velocity, is VF minus VI. And VI was 34 in this question, and so VF minus 34, I can put that in instead, because again, that's what this is. Delta V is VF minus VI. So if I do that, I need to go ahead and multiply on the left-hand side my negative 6,900 times 14.1, and that's going to be negative 97,290 equals, and then over here I still have this. You can distribute it, or we could just divide both sides right now by 3950, which is what I'm going to go ahead and do. And I'm going to rewrite this so that this side is now negative 24.63. It does have more decimals. I'm not writing them all out. Equals VF minus 34. Okay, from here I just add 34 to both sides. And I get a final velocity that is equal to 9.37 meters per second, or 9.369. Okay, do be careful about your signs here, because if you do forget this sign, you are going to get the wrong answer. Does anybody have a question about this particular problem? This one's one that sometimes is an issue for students. Okay, then we're going to go ahead and move on. This is the cannon one I think that somebody asked about a minute ago. It says, a 45 kilogram cannon launches a 118 gram cannonball horizontally at a speed of 41 meters per second. With what speed does the cannon move? When we talked about the cannon firing a cannonball, we talked about how we have equal and opposite forces. It's a force pair. The force on the cannon equals the force on the cannonball. We talked about how because that collision, or really explosion in this case, takes the same amount of time for both of them, that means force times time equals force times time. They have equal impulses. They have equal forces. They're both opposite, but equal in magnitude, equal changes in momentum. Okay, all of those things are going to be true in any collision. Every single collision, if it's a bug with a windshield, if it's two cars crashing, if it's two people pushing off of each other, if it's a cannon firing a cannonball, it doesn't matter. Every single collision, your forces will be equal and opposite. Your impulses will be equal and opposite. Your changes in momentum will be equal and opposite every single time. Okay, what's not going to be the same is the accelerations, because their masses aren't equal. And thus their changes in velocity won't be the same either. Okay, but those other things will be equal. It's all in the notes if you want to go back and look at it, but let's go ahead and solve this particular problem. Because I know that they're going to have equal, equal changes in momentum, okay, because I know that those are going to be equal because I have equal forces and equal times, that means that I can set momentum of the cannon equal to the change in momentum of the cannonball. Okay, again, this all goes back to those notes, but because we have equal changes in momentum in any collision, doesn't matter what they are, because those are equal, we can say, hey, the magnitude of this equals the magnitude of this. Yes, the direction's different. We're just doing magnitudes here. Okay, and so if I look at this, my cannon is 45 kilograms. It has a change in velocity that I need to figure out. That's the one I want, is how fast the cannon moves. The cannonball has a mass of 118 grams. That is a problem because that is not the correct unit for us to be using. You cannot plug in numbers if they don't have the right unit. Grams must be converted to kilograms, which means that the mass of this is not 118, but rather 0.118 kilograms. Divide by 1,000. Okay, so that is my mass, and then my change in velocity of my cannonball is 41 because it starts at rest. Before it gets fired, it's at rest. Now it's going 41. Okay, now this is not a particularly difficult problem to solve from here, if you can get everything plugged in and if you recognize you need to change your units. Yeah.
Can I forgot my AirPods case over here?
You're welcome to look around. I have not seen it. All right. So if we multiply 0.118 times 41 and then divide by 45, we are going to get delta V is equal to 0.1075 meters per second. And that is the change in velocity, but because these things both started at rest, that also happens to be its final velocity. So the cannon should not be moving very fast because it has a lot more mass. Okay, we've talked about that with the bug hitting the car. It's the same concept. And the answer is going to be this last one on my screen, 0.107 meters per second. It's not rounded right, but it's the right answer. All right, this one I found to be slightly confusing because the numbers were taken out of the question and yet there were numbers in the answers. Hopefully you did not pick anything with a number because you couldn't calculate it. Now this picture and this question comes from your problem set. If you want to go back and look at it in the problem set and see how to do it with the numbers, it's already there. But this is a concept question, and it says in the figure the figure above depicts the before and after collision speeds of a 0.41 kilogram toy car that undergoes a head-on collision with a wall. In case A, it bounces back. In case B, it crumples. Where is the change in velocity, or what correctly describes a change in velocity? Again, you cannot pick any of these things. We don't have numbers, so we don't know what the change in velocities are. So I probably would have changed those choices so that they didn't have numbers in them, but it's okay. So that leaves us with two choices. Car B experiences a greater change in velocity than car A, or the exact opposite. Car A is a greater change in velocity of car B. And guys, in the case of car A, if we put some fake numbers to this for a second, we could say that car A is initially going, let's say 8 meters per second, just making up numbers, it doesn't matter. And now it's going 3 meters per second. Okay, this is not a change of 5. Okay, it's not 8 minus 3, that's not what it means. Because this isn't 3, it's -3. This car doesn't just go from 8 to 0, it goes past that. Think of it like a number line. Okay, where you have 0 and then you have negative numbers over here, negative something, positive something. If you're going from 8 to -3, again, you can get this by doing final minus initial. -3 minus 8 would be -11. That's going to be important for your math, because you will have a question on your test where something does change direction. Please don't look at this and say, oh, the change is 5 or -5. Okay, you need to take into account the fact that this is going -3, and so the change isn't 5 because it's not going from 8 to 3. It's going from 8 to -3. The change is -11. Okay, if you have something that bounces, and I know there weren't any numbers in this question, but if you have something that bounces, I just realized y'all couldn't see the number line I drew. Not that it matters, it wasn't very pretty. But if something bounces, your change is going to be greater than if it sticks. Your change in velocity is going to be greater. Okay? If it sticks, it just stops. But if it bounces, then you're going, past 0 into the other direction. All right, so the answer to this is that car A will have a greater change in velocity than car B. This is the one that only has one answer, but this question gets to the root of some common misconceptions. You will see it again. This question is on your test, and I think it's on there more than once. So you need to be able to explain it too. Okay, let's read it. It says, which of the following correctly describes the reason padded dashboards are used in cars? This question could easily say, what describes the reason airbags are used in cars? Or what describes the reason that you put a bumper on the front of your cart in your lab last week? Or if you're in Physics L, why did you surround your egg with cotton balls? Okay, why do these soft things exist in these collisions? Okay, and so what you want to think about here, the impulse and the momentum are going to be unaffected by this. The impulse of a collision is not going to be affected by your airbag. It's not going to be affected by your crumple zone. The impulse is going to be determined by how fast you're driving and how heavy your car is, and that's it. Okay, and so that's going to be the same. What these engineers do is they try to add these things in to increase the impact time so that the force is smaller. When you guys looked at the graphs in your lab, those of you in Physics K, you had that kind of bell curve looking graph for your crash. You wanted it to be spread out more. You wanted it to take more time because that brought the maximum down. Okay, and so that's what you're looking for here. You want to increase the time of the impact in a collision. because when you increase the time of the impact, the force will be less. And that's what you want, is less force. But it does not change the impulse. It does not change the change in momentum. Okay, all it does is it decreases the force. If that was a choice, it would be true. But it does that by increasing the time. This was in the notes over and over and over again. You can go back and look at it there too. It's also in your problem sets. But you do need to remember that relationship between force and time. In fact, I wrote it like this in the notes. Force, time. Y'all remember that? Okay, same thing. This would be something hitting an airbag. This would be if you hit the windshield. It happens in a very small time. It's very hard. It doesn't have give. This one has a lot of give, so it lets you move forward more. It reduces the force. This one's got a big force. Okay, so again, remember that. It's going to be on your test multiple times. All right, this one just asks what velocity this car would need to have the same momentum as this truck. That's pretty easy. Again, momentum is just mass times velocity, so you would multiply 2550 times 27.93 and get a momentum. And then to make the car have the same amount, figure out how fast it has to go. Okay, so you would take that momentum and divide it by this particular mass, which I haven't done yet. So let's see what it is. Okay, so 2550 times 27.93 means that truck has a momentum of 71,221.5. If I want to know what velocity the car needs, I just need to take that momentum, because momentum is still equal to mass times velocity. I have the momentum, I have a mass, I can find the velocity. Take my momentum, divide it by this mass, 1020, and it gives me a velocity of 69.825 meters per second. Oh, there's a direction here. Let's be careful. Same momentum. This one was north. This one needs to be north too. Okay, momentum is a vector. It does have a direction. All right. This question is your FRQ. I'm telling you right now. Different numbers, different scenario, but this is your FRQ. So you might want to listen to this one. Okay, at least one of them. You're actually going to have two. One of them's written. And that's why I said you might want to pay attention to this question about padded dashboards, because you're going to need to be able to explain something like that too. Airbags, all that. Okay. At least something along those lines. That's not exactly. All right, so by the way, this question was in our notes at least 2 or 3 times, and it was in your problem sets at least 2 or 3 times. So this is like the 6th or 7th time that you're seeing it, okay? It says, a baseball player with a mass of 76 kilograms slides for 2.6 seconds as he comes into home plate, where his final velocity is 0. The coefficient of kinetic friction between the player and the dirt is 0.594. It gives us a free body diagram. This particular diagram is actually correct. The ones in the problem set had like different diagrams and you had to say what was wrong with it. But if you have something that is sliding to a stop, okay, whether it is a baseball player, whether it is a hockey puck, whether it's a guy on a scooter, it's a book sliding across the floor, whatever, there will be no forward force. They're just coasting. Okay, they're in motion, and the only thing that's happening here is friction slowing them down. Okay, so this is what your free body diagram needs to look like for anything that is sliding to a stop. Unless it tells you there's some kind of forward force, it looks like this. Okay, again, you need to be able to draw that. All right, so what is the change in the player's momentum as he comes to a stop? This has multiple parts, just like your FRQ. Okay, so change in momentum is equal to mass times change in velocity. It's also equal to force times time, depending on what information I have. I could use either of those, okay, because they're all equal to each other. So in this particular problem, I have a mass. I do not have a change in velocity. I have a final, but not an initial. Okay, however, and I don't really have a way to get the initial, at least not right off the bat that I see. However, I do have some information about force because there's a free body diagram there. And I know I can solve for a force because they gave me a coefficient of friction. and they gave me a time. So this is actually what we're going to end up using, and I can see that right away, but if you can't see that right away, that's okay. If you can't see that right away, then what you need to be doing is looking at the numbers you have and asking yourself, what can I do with this information? And if they give you information about a coefficient of friction, use it. Especially if they gave you a mass, because you already know how to find Fn. It's equal to Fg. You know how to find it. And remember, you can figure out that force of friction as long as you know your coefficient of friction and your normal force. Okay, so and we can find both of those things. All right, so let's do that. Again, I don't have a formula for Fg, but I do have for Fn rather, but I do have a formula for Fg. That's what we're going to do. We're going to solve for Fg. My mass is 76, gravity is 9.8, and if I find Fg, I'm also finding Fn. So 76 times 9.8 is going to be both Fg and Fn, and it is 744.8. All right, so now I have Fn. I have mu, it's in the question. I can find Ff. So now we're going to use this equation, and we're going to say that it's equal to, mu was 0.594. It's highlighted on my screen. Fn is 744.8. And if we multiply those two things together, it gives us our force of friction, which is going to be equal to 442.4112 newtons. Now I am going to go ahead and put a negative sign in front of this. My calculator is not going to get a negative number, but I'm going to add a negative sign because I know that friction's going backwards, opposite my direction of motion. Okay, so I have a negative tacked on here. The force of friction is going to be super important because it is your net force. There's nothing canceling it out. It is your horizontal net force. You don't have a vertical net force. And so this isn't just FF, it's also Fnet. And Fnet you can do some stuff with because that is what goes up here. You can't see what I just did right there in that equation. Okay, so F times T is impulse, but it's also change in momentum. And so now that we have a force, we can figure out our change in momentum because we can take that force, negative 442.4112, and we can multiply it by the time, the duration that this force is applied, which is right here, 2.6 seconds. Again, this is just like your FRQ. Please make sure you know how to do this. Okay, you have these questions in your problem set. Go back and look at them. They're also in the notes. All right, so let's multiply it by 2.6. And we're going to get this number right here. Technically, that's negative. I didn't type the negative sign in. Negative 1150.27 or 269. It's right here. All right. That is his change in momentum. What is the player's initial velocity? Okay, so we have our change in momentum. We know that his final velocity is 0. So if we want his initial velocity, okay, well then that means this change in momentum is equal to his final momentum minus his initial momentum, but his final is 0. So this whole thing is equal to his initial momentum. Okay, which means I can say negative 442.4112 equals mass times initial velocity. The mass of the baseball player was, I already forgot, 76 times V. Okay, and so that will give us his initial velocity. So if I divide the answer that I have by 76, oh, sorry, hold on. That was not the right number to use. Sorry, that was the force. I have it on my calculator, I didn't write it down. It was the 1150, I apologize. 1150.27 was the actual change in momentum. I didn't actually answer it. It was the product we got from that. All right, sorry about that. So we're going to take that number and we're going to divide it by the mass, 76, and we're going to get our initial velocity. And sorry, I guess this isn't negative anymore because we had it as negative equals negative. All right, so the initial velocity is 15.135 meters per second. All right.
What equation did you use for that one again?
So this is just momentum is mass times velocity. Because his final velocity was 0, it says he comes to a stop. And this was the change that we had. And actually the change was that is this 1150 number. You ended up with negative 1150.27 equals 0 minus pi. And so that means that initial momentum is this. And so then all I did was say 1150.27 equals mass times v.
Okay.
And I found VI.
What was like initial?
Yeah, that's for initial because the final's 0.
Oh, okay.
Yeah. And sorry if I confused anybody because I forgot to write down my number. Yeah.
You said this will be like the FRQ or something like this?
Yes. This is just what it looks like.
It's not like friction and everything?
It had friction in it.
Like, it will have friction though on the test?
Yes. Yes. But, sorry? It's basically the FRQ with different numbers.
And then you said the other ones would be like...
I'll show you the other ones in just a second. Yeah. Okay. Last part of this says how far does the player slide? So again, we know his initial velocity. We know his final velocity is 0. We know how long he's sliding for. I think it was that 2.6? I think it was. Let me double check. Yep, 2.6 seconds. Okay, so we have VI, we have VF, we have T. We can solve how far is delta X. And if I want to solve for that, I have to use a kinematic equation. I could find the acceleration first if I want to, but if I want to do this in doing less steps, I'm going to use the very last equation on my board over there, and that is this one. Delta X equals VI plus VF divided by 2 times T. Then I don't have to do any extra steps. It's all this one last calculation. So if I want to substitute in, that's going to be 15.135 plus 0 divided by 2 times 2.6. Okay, and that's going to give me my delta X. And so let's go ahead and figure out what that is. That ends up giving us a displacement of 19.676 meters. Or 675 is how she has it rounded. But that is how you solve that one, yes.
Oh, I just have a question for the unit 5 summary.
Okay. Give me a second. Let me pull up something else real quick. 502. I think it's in here. I think it's this one. I'm trying to remember which one it's in. So I know this question is in here, so I'm trying to look for it. It might not be in that problem though. It is not. I think it's in here. All right, I was going to show you the other ones that I was talking about. If I can find them. Okay, I found it. It's in 502.4. Come on. Let me type an ID in just so we can look at it. Okay. So inside of 502.4, number 4, same idea. You'll notice it's the same questions. What's the force of friction? What's the velocity after this time? How far does it move? Here's another one. with a sled? What's the change in momentum? What's the initial velocity? How far? Those are the same questions we just answered with a different scenario. And the free body diagram here, by the way, wrong. Okay, don't draw it like that. In fact, that's what it has you identifying. Here's another one. That's why I said there are 3 of them in here. Okay, in a row in 502.4. They're also in your notes. One of them was a warm-up question. So, and then there's a couple others. So you can go back and look if you want some more examples. You have them, but that is what your free response question looks like. Did you have a question?
Oh, yeah. Okay, mine was for the summary, though.
Do you want me to finish this first and then look at that, or do you want me to pull up the summary?
No, you can finish that first.
Okay. All right, this is the next question on that quiz. It says 2 graphs above show the change in velocity experienced by 2.68 kilogram rubber balls during a head-on collision with a wall. And again, this question came from your problem sets. You have seen this graph before. I think it was in 502.3, I think. It may have been in 502.2. But you've seen this before. And if you look, you can see from the graphs, in the graphs you can see the initial velocities of each, or you don't know what numbers they are, but you can tell that this one has a bigger change in velocity in case A than in case B, and they have the same mass. So if it has a bigger change in velocity but the same mass, then it's going to have a larger change in momentum. Okay, because that's the equation for it. So case A will have a larger change in momentum or a larger impulse than case B, because this one doesn't have as big a change in momentum. This both happened in the same amount of time, from 3 to 5 seconds for both of them. Ball A does accelerate more, absolutely. This is a velocity time graph. The slope is steeper. You can see it. Okay. Both collisions took 8 milliseconds. No, they did not. The collisions only where the slope is. Again, if there is a collision, there's a force, and if there's a force, you have to have acceleration. That's only the sloped part, and that's 2 milliseconds, or no, sorry, yeah, 2 milliseconds long. It's from 3 to 5, which is this. Both collisions took 2 milliseconds, and that should be it, because this is the opposite answers. So those 3 should have been what you selected for this particular question. Questions about this one? All right. Next one. A softball with a mass of 0.19 kilograms moves at a speed of 18 meters per second. Then the ball is hit by a bat and rebounds in the opposite direction with a speed of 16 meters per second. What is the impulse experienced by the ball? The number one problem students are going to have with this is they're going to tell me the change in velocity is -2. It is not. Okay, because it doesn't go from 18 to 16 in the same direction. It goes from 18 all the way to 16 in the other direction. Okay, it goes from 18 to -16. So that means that your change in velocity, if you miss this, that's probably why. Okay, again, draw a picture if you need to, but it's doing this. Okay, it starts out at, I didn't draw those to scale, but it starts out at 18 and it ends up at 16 in the other direction. So my change in velocity is going to be -16 minus 18. Again, it's not going to be 2. It's going to be -16 minus 18, which is going to be -34. That's your change in velocity. Again, if you missed it, this is probably why. Okay, I don't know if you missed it or not. We'll figure it out. What's the impulse? Again, impulse is force times time, which I don't have, but it's also mass times change in velocity. There's my change in velocity. My mass is 0.19. It's in the question, so I just need to multiply my -34 times 0.19, and I get -6.46 Newton seconds. That should be the answer you selected here. Questions about this one? All right, next one. While at the circus, you see a tightrope walker plummet 25 meters. Fortunately, a safety net below catches her. Which of the following statements is true regarding the force she would experience if she lands on the ground versus a safety net? This is the same idea as hitting an airbag versus hitting the glass, or as your bumper project with a bumper versus without. It's the same thing. The forces are not equal because the times are not equal. Same concept we've talked about over and over and over again. You're going to experience more force hitting the ground because the time will be instant, whereas hitting a safety net, there's give to it. It's going to stretch with you. You're going to keep moving for a little bit longer, and so there's going to be more time and thus less force. So the ground will have more force than the safety net. Okay, that's that one. That's what you should have selected there. All right, 3 physics carts can only move along a straight level path. The motion of each cart is plotted on a position time graph. The magnitude of momentum of the physics cart increases in which case? All right, so basically if we want the momentum to increase, that means we want the velocity to increase. And so the question is, which one of these has an increase in velocity? These are position time graphs, and the slope of a position time graph is your velocity. Therefore, if you want your velocity to change, your slope must change. Only one of these has a changing slope, and I know that because it curves. Okay, the only one that has a changing slope is this third graph that has a curve because the slope starts out more shallow and gets steeper and steeper and steeper. This one has a constant velocity. This one's not moving. Okay, the only one that has an increase in momentum because of an increase in velocity is graph 3. Are there questions about this particular problem? Okay, we're almost done. Which correctly describes the differences between inertia and momentum? These are just definitions. The first one on my screen is actually the right one. The definition for inertia, it is a measure of mass, whereas momentum is a measure of mass in motion. That's just definitions. Memorize them though. I think they might actually be on your test. So memorize it. I don't think we have questions about it since it's just a definition, but does anybody have a question? Okay. What would happen to an object's momentum if its velocity were doubled and its mass were doubled? Again, momentum is mass times velocity. So if we were to double both of those things, and again, you can use fake numbers here. You can say, oh, my mass is 1, my velocity is 1, my momentum is 1. Now let's try 2 and 2. Okay, it's going to change by a factor of 4 because you're changing both of them. If you double both the velocity and the mass, you're going to double it twice, and doubling it twice is a factor of 4. Okay, 4 times as much. This one, I think, is supposed to say 1/4. I'm not positive, but it just says 1/, but was not your answer, so it doesn't matter. All right, I know how much you guys love this question. Y'all have seen this before a couple times. It says the graph below shows the net force acting on a bowling ball as it rolls down a hallway for 6 seconds. Determine the impulse affecting the ball for the 6 seconds of the motion graphed above. This is what you did in your lab. The impulse from a graph that looked like this, your graph looked like this. I mean, it was curved, but it looked like this. The impulse is the area. So if you want to know the impulse, find the area. Area of a triangle, 1/2 base times height. Okay, this one has a base of 6 and a height of 3. 6 times 3 is 18. Half of that is 9. Your answer should be 9 Newton seconds. You could be asked a question where you have a graph like this. You have to get that and then do something else with it. Okay, so just be aware. That might be a step as part of a problem. I don't know if it is on a test, but it could be. Questions about this one? Last one. We're almost done. 2 vehicles, a semi-truck and a small car, are traveling toward each other and then collide, bouncing off of each other. Which of the following statements correctly describe the collision? Select all that apply. Guys, please don't tell me that they have different forces. We've talked about this for 3 units now. Equal and opposite forces, it's a force pair. Don't pick that one. Okay, again, equal and opposite forces is also going to mean equal and opposite impulses because the times are the same as well. It's impossible for me to touch you and for you not to be touching me at the same time for the same amount of time. If you touch something, we're touching for the same time. As soon as I stop, it's not touching me either. So if the force and the time are both equal, because impulse is force times time, if these are both equal, then that is equal as well. In any collision, the forces will be equal and opposite, the impulses will be equal and opposite, the changes in momentum will be equal and opposite, always. Okay, as long as you're talking about a collision between 2 objects. Now, if we're talking about this car hit a wall and this one hit a cotton ball, not the same. But when we're talking about 2 objects hitting each other, okay, then yes. All right, so we're not going to say it's greater impulse. Same magnitude of change in momentum, that's true. Because they have the same force and the same time, they absolutely have the same magnitude of change in momentum. The car experiences a greater change in velocity. Yes, it would. because it has less mass. Again, if the impulses are equal, then that means the mass times change in velocity equals the mass times change in velocity. But the car has a small mass and the semi has a large mass. And for those to remain equal, this would have to have a very large change in velocity, whereas this one would have to be very small. Okay, so yeah, the bigger object accelerates less. Just like the cannon and the cannonball, just like the bug in the car, just like this particular example. We've seen it over and over and over again. So both of those two should be correct. The car will have a greater change in velocity and a greater acceleration for the same reason. Questions about this last problem on the quiz? No? Okay. Let me go ahead and, I don't even know how you submit this. Review, I guess. Finish. I don't know how it works. Okay, it doesn't even show me my grade, but whatever. We already know. So anyway, that was your quiz. So hopefully that helped, at least as far as the quiz questions go. If you guys have other questions about unit summary problems or anything else, please feel free to let me know, and we can look at those as well.